to the first video on radar. The acronym radar stands for radio detection and ranging. And back in the 1930s, radar was being developed to be used in World War II. At the end of World War II, they realized that radar not only detected aircraft and other objects, but also detected precipitation. So they developed radar for looking at weather kind of after World War II. This was in the late 1940s into the 1950s. Finally, into the mid-1950s, the first network of radars was set up across the United States to detect precipitation, thunderstorms, snow, rain, showers, and that was used at larger cities. Later on, they expanded that, and now we have a network that covers the entire United States. So the basic idea behind radar is that it sends out a electromagnetic wave through the atmosphere, and in pulses of energy, little pulses. So it's not continuously radiating, but it's kind of like a switch on a light turned on and off very rapidly. So rapidly it's measured in microseconds. So that pulse of light, well, it's not light, but pulse of electromagnetic radiation travels through the atmosphere, strikes objects in the atmosphere, and then comes back. Actually, the energy is scattered in all directions, but what we measure is the backscatter energy. So basically what radar can measures how much energy or the power coming back to the radar, how much is reflected back off of the objects in the atmosphere. Also, if you know where the radar is pointing, you can measure the azimuth, and also the range is the distance and the time that it takes for the radar pulse to travel out to the object and then reflect back off. And of course, radio waves travel at the speed of light. And then also elevation. In other words, if you know how high your dish is pointing above the ground, you can measure that elevation angle. And also that gives you more or less the altitude in feet or in kilometers above the ground. Then also, just by watching the echoes move from sweep to sweep, you can see how the whole aggregate moves. In other words, all of the precipitation moves. But then also we have more detailed measurements using Doppler radar, where we can look at the velocity structure within the phenomena. So radar radiates in the microwave spectrum, which is a little bit longer than infrared waves, but a little bit shorter than radio waves. And microwaves are the same frequency or same wavelength as your microwave oven. That's why they've given that the name. There are a lot of different wavelengths within the microwave, and they're given different letters to indicate what band, or in other words, what frequencies the energy is being transmitted at. We tend to look at it as wavelength, the wavelength, or how long the electromagnetic wave is. For radar, radar waves have letters that indicate what type of radar it is. And they go from L to Ka. We are just going to talk about L through X. That's what weather radar is used for. So we're looking at L-band radar, which is, there's a range from 30 to 15 centimeters. So you don't have to worry about that, but it's about, on average, it's usually called the 20 centimeter radar. S-band radar, the wavelength of the waves is about 10 centimeters. C-band is 5, and X-band is the shortest at 3 centimeter wavelengths. So the idea behind radar is that a pulse of electromagnetic radiation is traveling through the atmosphere and is scattered in all directions. Some of it is scattered back. And the amount that is scattered in whichever direction depends upon the size of the object and then also the wavelength. So we, our researchers have found that the longer the wavelength, the less radar energy is scattered by raindrops. And the shorter the wavelength, the more energy or power is scattered by the raindrops, and they're sent in all directions. We can measure that backscatter, how much comes back. So there have been a number of different radars that have been developed for different purposes. As I mentioned, longer wavelengths tend not to scatter energy from cloud droplets. So the radars that are in use today, L-band radars, which are 20 centimeter, we mentioned that already, typically are used for air traffic control, and they're not really designed for weather radar, but you can see a little bit of precipitation, a little bit of weather echoes on airborne, or not airborne, but L-band type radars, air traffic control radars. These are similar to the ones that are all across the United States, the ASR-9s that are used for air traffic control purposes. S and C band radars, these are 10 or 5 centimeter, are designed specifically for ground weather radar. So these are your WSR-88Ds or your terminal Doppler weather radars. We'll talk about what those mean. But those are tuned to look at precipitation. That is just the right size. 10 centimeter or 5 centimeter is perfect size for looking at precipitation-sized particles. They scatter a lot of energy back to the radar. And then finally, your X-band, which is a 3 centimeter radar. It can also detect precipitation pretty well. So they've used that for airborne weather radar. Since it's a smaller wavelength, it can see more smaller droplets, and also, for that matter, even some cloud particles. So the reason that we use different wavelengths, of course, is because we get to look at precipitation. You know, some radars are tuned just right for precipitation, like the 5 and 10 centimeters. But it also comes down to the antenna size. The smaller the antenna, or the shorter the wavelength, the smaller the antenna that you can use. And the bigger the wavelength typically requires a much larger antenna. So you can see on the left in this picture, the airborne weather radars are usually 3 centimeter because they require a smaller antenna. Whereas ground-based weather radars, since they're a longer wavelength, require a much, much larger antenna. Another interesting fact is that the antenna size determines the radar beam. So how wide is the beam? And the idea is you want a very narrow, very focused beam, much like a flashlight focuses light. The same thing with antennas, they focus radar energy. So with a larger diameter radar antenna, for example, the 12-inch antenna, you have an 8-degree radar beam, which actually is very, very wide. And you want a narrow one so that you can get good resolution when you're looking at thunderstorms or other types of precipitation. You get to a larger size, 14-inch diameter antenna inside of an airplane. An X-band radar is 7.3 degrees. Even larger, 18 inches takes it down to 6-degree beam width. So here's a table that shows all the different antenna sizes. Of course, larger airplanes can have bigger antennas. You're talking about a 747 has about a 30-inch antenna. Sometimes they use an X-band, sometimes they use a C-band. There's an advantage we'll talk about with C-band. X-bands tend to attenuate more, C-bands don't. So some basic things that you need to know about radar. Number one, air traffic control radars aren't very good at detecting precipitation because they have a longer wavelength. Remember, that's the 20 centimeter radar. And then ground-based weather radars, your S and C band that the National Weather Service operates, they do very good. They're tuned just right to precipitation-sized particles. And then airborne weather radars, or X-bands, are also very good at looking at precipitation, but they tend to lose radar energy when trying to look behind other thunderstorms or things like that, what we call attenuation. A few terms that you should be familiar with: target and echo. Target is, in other words, a group of objects or an object that reflects radar energy. That's our target. And an echo is the actual radar energy that is reflected or coming back, which is backscattered. Another term you probably heard of is Doppler radar. Meteorologists call it coherent radar. And that is a radar that is able to measure the change in the frequency. You send a radar pulse out at a specific frequency, a specific wavelength. It comes back at a different wavelength. And we can measure that. The reason the wavelength or the frequency changes is because of the motion of the targets. If they're moving at one direction, then you can either add or subtract that velocity to the wavelength, and it actually changes the wavelength. So that's how we can tell if precipitation is moving towards or away from the radar within a thunderstorm. Also, another thing that we can measure is the spectrum width. And the spectrum width is how the droplet speeds are distributed. And that'll tell us a little bit about precipitation turbulence within a thunderstorm. And also it helps us identify different types of objects in a thunderstorm. And then finally, dual polarization is another term that is used for radar. The radars across the United States, the network is now a dual polarization network. They did that back in 2010. And what dual polarization does, it sends out a pulse of electromagnetic radiation in one plane, and then it can do it in the other. And then comparing the reflectivity in one plane versus the other tells us something about the precipitation-sized particles. Because raindrops actually are flat. They're not teardrop, but they're actually flat. So if you can see the radar reflectivity in one direction compared to the other, you'll see a difference. Whereas hailstones are more spherical, and they'll have about the same reflectivity in either plane. But also, it helps us detect other things like birds. It helps us figure out where birds are, because birds really look kind of funky to the radar. That's all I have for you for this first video. Please listen to the second video. I hope you enjoyed it. Bye.